The quadratic equation is easy to solve, but sophisticated enough to provide insight into the energetic stability of chemical bonds, to allow for the calculation of the pure frequencies of oscillation of coupled springs and masses, and to allow us to model the dynamics of the abundances of molecules in biological networks. In this video, we will graphically illustrate what it means to solve the equation ax squared plus bx plus c equals 0, and then walk through an analytic derivation of the well-known quadratic formula. To illustrate the meaning of solving the quadratic equation, we first need to provide a graphical interpretation for quadratic functions. The constant c corresponds to a horizontal bar. If the constant c is non-zero, the red bar is shifted vertically away from the x-axis. In this example, the constant c is negative, corresponding to a red bar below rather than above the x-axis. If the coefficient b is non-zero, the term bx describes a slanted line passing through the origin where x equals y equals 0. In this example, the coefficient b is positive, corresponding to a line that ascends rather than descends as we move toward the right. The slanted line corresponding to bx is added to the constant height c. If the coefficient a is non-zero, then the term ax squared traces out a bowl. X squared becomes larger in magnitude as x increases and moves farther and farther to the right of x equals 0, as well as when x decreases and moves farther and farther to the left of x equals 0. In this example, the coefficient a is positive and the bowl opens upward rather than downward. Adding the term ax squared to the sum of bx plus c that we previously plotted produces another bowl-shaped curve. The sign of the constant c determines whether the red dashed line floats above or below the origin. The sign of the coefficient b determines whether the slanted golden line ascends or descends toward the right, and the sign of the coefficient a determines whether the blue bowl-shaped curve opens upward or downward. Now that we understand how to graph quadratic functions, we can explain what it means to solve the quadratic equation. The example curve y quad on x versus x that we have plotted intersects the horizontal line y0 on x equals 0 at two locations. Solving ax squared plus bx plus c equals 0 means finding the values of x where the blue curve, which corresponds to ax squared plus bx plus c, is equal in height to y0 on x equals 0, which traces out the x-axis. The values of x highlighted by the magnifying glasses are called roots or zeros of the quadratic function. As the figure shows, one way to solve a quadratic equation is to make a plot of the quadratic function under study, and then to circle any locations where the curve intersects the x-axis. Another way is to use the quadratic formula, which we will derive on the next slide. The roots of a quadratic function can be determined analytically in terms of the parameters a, b, and c as follows. Assuming that the coefficient a is non-zero, divide both sides of the equation by a. Dividing 0 by a simply gives back 0. We copy the preceding equation without doing anything. And continuing to do nothing, so to speak, we add and subtract to the left-hand side of the equation the same quantity, namely numerator b over denominator 2a with this entire fraction squared. We use yellow highlighting to group the leading term x squared, the linear term bx over a, and the positive copy of the constant term we just added. The yellow terms are equivalent to a square of a sum, namely the sum x plus b over 2a. The strategy of adding and subtracting b over 2a quantity squared, so as to be able to reveal the square of the sum, is called completing the square. Before continuing with this analysis, please pause the video to verify that completing the square works, and please check that you are comfortable with the term accented with white font, that being the square root nested within the square. We factor the difference of squares into two pieces. These factors look similar. Both factors have the same yellow piece, and both factors have the same white radical. The distinction is that one factor has a plus sign where the other has a minus. The equation requires that the product of the factors be 0. This implies that a factor is 0. Either factor will do. To notate this situation concisely, we use a minus plus sign. Move the yellow b over 2a and the radical to the right. Write the expression out over a single denominator 2a to obtain the usual form of the quadratic formula. If a function, whose association rule is ax squared plus bx plus c, intersects the x-axis at 2 points, we can use the quadratic formula to find those roots. In this video, we graphically illustrated the meaning of solving the quadratic equation and derived the quadratic formula commonly used in courses in algebra. Later in this course, the quadratic formula will allow us to study a quasi-species model, which describes genetic evolution. The quadratic formula will also help us to model the dynamics of the abundances of biological molecules inside cells.